Let's do some plug and chug binomial problems. If I'm given some information like my n is equal to 5, my p is equal to 0.2, then tell me what is this. And first of all, let's talk about how we even read that statement. P of parentheses x equals 4, close parentheses. The question mark is just part of the question, so we'll just ignore that part. But the big P here, that's saying what is the probability of everything inside of my parentheses. So what is the probability or the likeliness that x is equal to 4? That's all this is asking, is in this scenario here, what is probability x is equal to 4? Now, n equals 5 means there's 5 trials. So whether it means you're going to sample 5 people or you're going to take 5 free throws, your number of trials is 5. P of 0.2 means that your probability of succeeding is 20%, 0.2. So what is the probability that we get something that's exactly 4? I'm going to list out all the possible options. Now, when it's a PDF situation, an equal sign situation like this, you won't always need to draw this, but just to be consistent with what I'm going to do in the other problems, I'm going to list out all the possible things they could do. You get a 0, a 1, a 2, a 3, a 4, or a 5. What we want to know is what is the probability of getting a 4, exactly a 4. And to do that, we use our binomial PDF. I'm going to write that out. Binomial PDF for a single value. Whenever we see an equal sign like that, or we're only looking for a single number, it's always going to be PDF. So I go to my second vars, I go up towards my binomial PDF, and I type in my n, comma, my p, comma, my value of x, so 4. And if I do that, 0.0064 is going to be my answer. And what that means is the probability of getting 4 successes in this situation is a little less than 1%, 0.006 probability. Next one, almost the same scenario, but this time we want to know what is the probability that x is less than or equal to 3. Now here's where that little drawing that I made before is going to be much more helpful. So let's go ahead and do that. 0, 1, 2, 3, 4, 5. You can succeed 0 times at the minimum. You can succeed 5 times as a max, and anything in between is also possible. So in this one, we want to know x is less than or equal to 3. Well, 3 is less than or equal to 3, and so is 2, 1, and 0. So I'm going to include all these numbers, and I'm going to draw a little box around them. So that way I know, I remember, this is what I want to find. I want to find the probability of these 4 numbers. Now I could take the PDF of each of these 4 and add them together, but a much faster way to do it is to take the highest number here on the left, this 3, and do a CDF, a binomial CDF. So I'm going to do binomial CDF of n, which is 5, comma p, which is 0.2, comma x, the highest number on the left side here, which is 3. So let's crank that out real quick. Second vars, go up to my binomial CDF. Remember, C stands for cumulative, and you're accumulating multiple values here, so that's why we do CDF. We do 5, comma 0.2, comma 3, we said was our magic value of x. We get 0.993. Okay. 993. Seems like pretty high probability, but then again, this situation, you only have a 20% chance of success, so to get 0, 1, 2, or 3, that's going to pretty much include most of the people that would ever happen. It's very unlikely that someone's going to get a 4 or 5. So the next one, it says, what is the probability that x is greater than 3? Well, that seems really similar to what we did, except it's going to be a little bit trickier. We list out all our values. And then we draw a box around the things we want. Well, 3 is not greater than 3, but 4 is, and so is 5. So we want to know the probability of these two. Again, we could take the PDF of each of those values and add them together, but what we want to get used to, especially when we start dealing with bigger number situations, is how to do it with CDF. Calculators only can go to the left with the binomial distribution. That's all they can find the probabilities for is on the left side. But we have data on the right. If you remember, the data on the left and the data on the right, if you add up all the values, they're going to add up to 1. So if we know that left side plus right side equals 1, then we can figure out what the right side is based on just knowing the left side. So to figure out the left side, this area over here, I'm going to draw a red box all the way around it. To figure out that, we would do what we just did on the previous slide here. We do the binomial CDF of 5.2 and then 3, the highest number on the left. So we said this was 0.993. So this is 0.993. Then now we can figure out that plus what equals 1. Well, 1 minus 0.993 is going to give us 0.007. So the answer to this question is the thing I drew in blue at the very beginning here, this part. What is the probability of getting those values? It's going to be 0.007. And we'll see another example where it's flipped like that in just a moment. N is P, P is N is 5, P is 0.2. What is the probability that X is less than 2? List out our values. And the probability that X is less than 2, well 2 is not less than 2, just these two values, 0 and 1. We're going to do a CDF, so binomial CDF of this one here, and we do N, comma, P, comma, our highest value on the left is going to be our X, so we'd write 1. Now you might say, oh, but it says 2 up here, why don't I write 2 in there? I would recommend you just cross that out, because if you cross that out, then you are going to be able to use your picture to help you out. So if you correctly draw your little diagram, your list of numbers here, you're going to find that that's much more helpful than the original problem. So sometimes just crossing it out or hiding it or forgetting about it, whatever it takes, might be a good strategy for you. I'm not going to punch this in my calculator right now, but that's what you would put into your calculator to get the right answer. And then this last different scenario that we could potentially face. We have, again, 0, 1, 2, 3, 4, or 5 possible number of successes. Want to know the probability that X is greater than 1. 1 is not greater than 1, but 2 and everything above it is. And since our calculator can't go to the right, again, we're going to go and figure out the left side. So the left side is going to be a binomial CDF, and that is going to, again, always use our N, comma, P, so 5.2, and then our X value is always the highest value on the left. So in this case, it's going to be 1. That will give us the area in red. If we want to get the area in blue, then we need to take 1 minus whatever we get here. So 1 minus the binomial CDF of 5.21. And that then will give us the area in blue. So this one I'll go ahead and do in my calculator real quick just so we can see it. We got our dister, we go down to binomial CDF of 5, comma, 0.2, comma, 1. And then we take 1 minus the answer that we just got. So 0.263 is our answer that we want. 0.263. One thing that we didn't talk about is what do you do if you have a really long list of numbers? Let's say n is equal to 180. And we'll just make up some other values here. P is 0.3. Find the probability that x is greater than 40. If you have n equals 180, you're not going to list out the numbers 0 to 180. That would take forever. So instead, you just want to get the values really close to this area of interest, this 40 here. So I'm going to start my list at 0, and then I'm going to immediately throw in some dots, and I'm going to continue numbering one below this value, right at this value, and one above, and then dots all the way to the end. The reason I do this is it's pretty easy for me now to draw any picture. So in this case, x is greater than 40. Picture is going to look something like that. If I had x is less than 40, picture would look like this. And then I'd know to put 39 in my calculator. It says less than or equal to 40. Do that. Greater than or equal to 40. Do that. So using this way of drawing it is very flexible. It lets you see all the information you actually care about. And because it's very compact, you only really are writing 5 numbers each time. So I think it's a pretty good method.